Start, yeah. All right, well, all right. Hey, it's a small gang here, so um, let's just dive right into it. So we have Linux Backwards project started in 2007. Um, it's now folded under the Linux Foundation. Some of you guys should already know this. Have you guys heard of this project? I mean, this is only a few of you guys, so are you guys familiar with the project? Obviously Jeff would, but maybe at least I think. uh, anyone not familiar with this project? Okay. So it's now folded under the Linux Foundation Backports Working Group. We basically strive to backport the kernel automatically. We have stable releases. We also have daily Linux Next releases. And we backport towards a series of the latest supported kernels. Contrary to your Linux distributions, basically try to backport to one specific kernel release. So when we provide a release, a tarball, you download it and you compile it. Basically, it should compile to a whole series of supported kernels. We backport, so this is what I was mentioning, how does this thing work? This way or this way? Basically, it's stable and also Linux Next daily releases. So basically, whenever there's a release by Linux on an RC, there's a release made with backports. When there's an RC2, another release. When Linux kicks off the dot release, the final release, another release is made. When Greg picks it up and basically releases a point stable release, another release is made. And every day, we basically make releases based on Linux Next as well. Well, so Linux Next, think of this more as a development platform of how we backport, and we basically, the master branch of the backport skit tree works off of Linux Next. So think of it this way: if we want to backport things, make our work less, what we do is we basically backport always on Linux Next. What happens eventually is that we basically branch out from a specific Linux Next tag that we backported. So for example, during the merge window, Linux Next doesn't move much, right? So we should be able to, at that point, then branch off and create a stable release on backports that will allow us to backport the stable release that Linux just released. There's some discrepancies, obviously, because Linux at times will not merge some components that were in Linux Next. So in those cases, you may have to revert some changes. And it's happened, but it's not that frequent that we actually have to do that. So I'll go into some of these details. Sure, no worries. We backport over 800 device drivers now. We stopped counting. At this point, it's just too much. Then we used to have stats and all this fun stuff, even though the amount of lines of code that's required. We just don't do that anymore. We had to start making compromises, though, because we started just backporting too many things. So, for example, DRM was backported. This actually started as an idea through Google Summer of Code. It was actually a student that I mentored who ended up backporting DRM drivers. This was, of course, considered a bit kind of crazy, but a student managed to do it, and we carried support for that. It did work for a while. We removed that, given the fact that there was lack of interest on Linux distributions to actually embrace backports for their own GPU drivers. I had hoped that essentially some Linux distribution might notice that we did the work for them and essentially that they could just pick it up, but no one really picked up on that, so we just removed them. And the reason is that it was a bit complex to backport GPU drivers, so we decided that it's just best not to carry anything that we don't actually have any support for, either in the Linux distribution front or any developers engaged. In this case, it was a community, Google Summer of Code project, and it worked out well, but it still incurred some effort on our part. So we don't have users, we're just not going to backport it. And the reason, again, is that we started growing exponentially, and we need to start scaling down in order to make things work more efficiently. We then also took another compromise to basically remove support for older kernels. We now only support up to 3.0 kernels. This, again, was just because we backported down to 2.625. every single Linux Next released or stable release, we backported down to 2.625, for example. So we just needed to start it to make compromises. The carrot that we told folks that we were engaging with is that if you essentially use the upstream model and work with the upstream model, we'll backport your device drivers for you for free. And essentially you get the bonus points of being upstream and also giving customers packages, for example. This was primarily for silicon manufacturers who essentially have to do all the work that essentially a Linux distribution typically has to do. We have 3 core developers, 2 co-maintainers. Right now it's just Haukas and myself. Haukas is doing most of the work these days. We backport all these different subsystems. Now, I like to get into the use case of backporting with Coccinelle. The use case that we have is very different of how you would embrace Coccinelle for usage on development as a regular kernel developer doing evolutions. You essentially, if you're working with Coccinelle to evolve the Linux kernel, you might use it once or twice a day or a month. For backporting, we essentially use it every day. We're also going to use it to apply the rules against all our device drivers for every single rule. So this is what people typically do to backport. They just if-def code. This is the second hunk. Are you guys familiar with this? So this is basically just the net device ops, right? So issues with this strategy is long patches. It's hard to review. Quilt, refresh, can fail. New driver gets added. Basically, you need to do the same if-def. Can we do better? Yes. We're lazy. There's only so many of us. We're backporting for all supported kernels. We need to scale. No one wants to do backporting. So solution, why not stuff this stuff into some sort of helper? And basically also a backport module. So this is what we ended up with as a one step to evolve backporting. Gains in this is that it requires splitting up the patches that you need to backport atomically. Each patch for one single respective upstream commit, that's essentially one collateral evolution that you backport. Now this becomes easy if you track Linux Next daily. If done properly, some Linux Next updates require 0 changes to upkeep backport to compile on all supported kernels. It's when we realized that this was one step closer to allowing us to backport automatically that it might be possible. So the new goal is then to tell kernel developers that kernel developers should ideally not have to worry about backporting and just work upstream. Current metrics is about 7 to 10 manual fixes on patches if you use the strategy based on Linux Next. Sorry, based between one stable release to the other stable release. Is that clear? So if we use this strategy, when from jumping, let's say 316 to 317, if you use this strategy, you would only have to go and fix hunks where quilt might fail, for example, on about 6, 7 to 10 times during the entire Linux Next releases. Just want to make sure that people understand this. Can we do better? No, not yet. I haven't gotten into Coccinelle yet. I'm trying to explain how we evolved from one methodology to another methodology. Now, the question is, can we do better? And obviously, the next step is Coccinelle. So you use Coccinelle, this is what you end up with for backporting that. Fortunately, now you all know Coccinelle, so I won't go into the details of explaining this, unless there's any questions. Anyone? Questions? Okay. Now, if we had a static inline upstream in the Linux kernel, that basically would then just have to be stuffed into our header files for the older kernels. And then you don't even have to use this Coccinelle file at all. Does that make sense? This is really important. That's correct. Does that make sense, guys? All right, so basically what I'm saying is this. Think of it this way. We had this nasty, hideous if-def nightmare, right? And then we evolved this into a wrapper that we ourselves provide now with a static inline that does all that work for you. The static inline is not upstream. That's all we would need. We would need a static inline upstream in the kernel that would provide this for us. And then when users are using old kernel, they'd basically, when they compile, they would get a header file that would basically port and add that functionality for the older kernels. And it basically would work, it'd basically implement this other crap right here. If it's an old kernel, then it would do this instead of doing this, which is now upstream. Does that make sense?
But someone still has to write that.
Yes. Please bear with me. I want to go through a lot of slides here. Okay. Just need to make sure that people understand this. So obvious gains. The obvious gains are you formalize the backport for one collateral evolution, easy and faster to review if you understand SMPL. So that's a problem unless you understand SMPL. You avoid hunk conflicts. So refresh is now magical. That was easy, but how about the hard stuff? The following implementation could have been optimized even further. Let's ignore that for now. So please bear with me on the implementation. This was done years ago. This is how we backported threaded RRQ support. So this is the old way of doing the backport. So essentially, you have a request threaded RRQ. Instead of that, for older kernels, we have a backported version of that, which we implement in a module. Okay? Or a header file. In this case, it's a header file. So I'm going to show you the actual implementation that we have. This is a backported data structure that we require now for older kernels. So we provide this for older kernels if you're less than 2.6.31, for example. Then this is the series of static inlines. So we have a compact IRQ worker, which basically just runs the thread, basically. You have the dispatcher, which is basically your IRQ routine now. You then have the this is the version of request-threaded RQ for the older kernels. You basically created a work queue here, single-threaded work queue, and then basically just queue the work. No, you just create it, and then just call request RQ. And that's pretty much it. Then there are the free version of the threaded RQ. It basically just frees the RQ, and then you also have to destroy it, the work queue. Then you have the synchronized RQ, which basically now you also have to cancel work sync as well. Does that make sense? So far, so good? Anyone? Okay. Backporting threaded RQ with SMPL. So this is what this looks like. You basically define a series of arguments. You have your original call, your if-defs, and then you add the other code. Now, pay close attention to this guy, private, and the declarations. T, and it's a pointer, and it's a private, it's a type. Pay close attention to that. Now, we also learned from Julia's talk that we shouldn't have to be stuffing all this stuff in, right? Because essentially these are non-modified. So that would change the pretty print stuff. So this could be simplified even further, but again, this is an old SMPL implementation. Then you also need a replacement for synchronized thread RQ, but you're going to if-def around it. Okay, so you're not removing it, you're if-defing around it. You also need a free RQ version for the old kernels, which is basically to free the RQ and also cancel work sync. Okay? The cool stuff is here, which basically required us to modify a data structure, which is basically the type the T, remember the original T? That was the private. You don't see the private being mentioned here, but we're using the T. So Coccinelle inferred the type for us and allows us to go and modify the header file with the data structure. I don't know if you guys think this is cool, but I think this is wicked fucking cool. Does this make sense? Does anyone, guys, any questions here so far? So again, let me just go through this really quickly again because it's important. Private right here, private right here. It's a type private, and we're just saying that it's some sort of type. That's all we're saying. Then later on, we get to modify the data structure. And Coccinelle inferred that for us, and we get to actually modify that data structure. Of course, I decided to add it to the top because sometimes data structures are added at the bottom, and we add some fluff, typically, right? Sometimes, not all data structures, but that's just the approach that we took this time. And fortunately, Coccinelle did respect my desire to add that specific struct at the top instead of the bottom as well. Does this make sense? Are you guys following with this? I'm adding a member to the private data structure that was passed as in the original request thread at our queue. So this private data structure is a private data structure to the device driver. It could be anything. I don't know what the hell it is. I'm just saying that there's a private device driver data structure there, and it's this argument. And I want the type. And now with Coccinelle's help, I want to modify that data structure and add this other data structure on top of it, which basically adds my fluff, which allows me to complete the backport. That's correct. I'm sorry, say it again. You know, this has worked. And the other thing too about this is that when we make releases, I was indicating how we make, you know, daily Linux Next releases and so forth. When we make a release prior to actually releasing the tarball, we do a compilation test of that tarball against all the supported kernels. So if there was a compilation issue, then we'd look into it. But from the code that I saw and that it produced, I didn't run into any of those issues. Perhaps there could have been some device driver that did some sort of casting that perhaps the rule wouldn't have picked up. But you know, so far for the device drivers that we carried, it seemed to do it effectively. So moving on. Problem: how are you 100% certain that your SMPL patch replacement was 100% accurate? We need a legacy patch series to SMPL equivalence proof. How the heck do we do that? So this is the proof in a generic algorithm. You get the code without modifications. You create a Git tree with it. You commit it. You apply the legacy patch series, right? You commit it as well. Then you revert that patch. But you don't commit that. Now you apply the transformation with the Coccinelle. And then you do git diff. If you see any difference, then basically the proof the proof is telling you that there's some changes there that shouldn't be there. Does this make sense? We certainly could have. I'm saying that when you apply Coccinelle, when I started working with Julia on this, so we cried a lot together on basically just the output on pretty print. And basically, Coccinelle just needed quite a bit of modifications. The amazing thing about this is that for backporting, that's the only specific change that was required for Coccinelle to help with backporting. So it's just pretty printing and making sure that the if-defs are aligned and respected. Yeah, so basically what ended up happening is that these if-defs sometimes appeared like over here. So just like 3 tabs. It thought it was code, for example, instead of some, you know, if-def. That's another way of doing it as well. And that's perfectly reasonable as well. But, if you do it with diff, you also get to see what happens. Now, and I'll explain why this is important too. It gets better, though. Kernel will reveal inconsistencies on the original backport. The new struct compat thread key was pegged on different private data structures on different device drivers. With Kernel, the backport was consistent. Another benefit. Kernel revealed 2 collateral evolutions were used on the patch, not 1 as it should have been. So, for example, one of the other collateral evolutions was the use of some obscure flag that's used for some weird device of some sort that tells the RQ handler to do something differently. We should have taken that out and actually added that as a separate atomic patch. It automatically backported this new collateral evolution 10 new device drivers. That was not the obvious gains of Kernel with backporting. And obviously this adds to the argument that you can backport even further and automatically with Kernel. Yes? So it compiled, but here's the thing. We have a kconfig option on backports that basically allows us to restrict to what kernel a device driver is allowed to be used on. So for those older device drivers, so for some of these device drivers, they weren't allowed to be used on older kernels, although the code was there to backport this collateral evolution. It basically was not something that would compile in for the user because we wouldn't allow that to compile in, but the code was there. So this collateral evolution was just backported, that's all. I looked at it, it looked reasonable. In fact, I compiled it, enabling it, and it worked too. But I'll get into why this is not enough later. So the amount of time to generate the backport was reduced as well. Using Kernel, even though it automatically backported this collateral evolution to 10 new device drivers. How and why? Any ideas? Any guesses? So basically, the patch application is serial. SMPL patch application is multi-threaded. All sets of target files are evaluated are split up by each CPU. So when you think of this, legacy patch application is just archaic and in the Stone Age. Does it scale? We're going to be running this daily. We need this to scale. It's not a question of whether or not it can scale. We need this to scale. It's a very different use case, and this is why I explained that earlier. We run this on a big Aryan server donated by HP SUSE Linux Foundation. It has 32 cores, 336 gigs of RAM. We use everything in RAM. We put Linux Next, Linux Stable, all the kernel sources from different kernels that we support. We do the code generation completely in RAM, and we also do the compilation test completely in RAM as well. So there's a script out there that basically enabled you to use Kernel's multi-threaded capabilities, and this is what this looks like. But it means that for each instance, you basically have to spawn a different PID for each bucket. So what this does, it tells Kernel, hey, we're going to split this between 10 jobs, and I'm the first one. And then the other one says, we're going to split it with 10 threads, and I'm the second one, and so forth. So you're spawning this off 10 times, for example. And this is just basically number of CPUs that you have. And that's pretty much it. So that was the original script. However, before we knew about the script, we basically just ran it with one single CPU. When we were testing this stuff, we decided that concatenating all the SMPL files that we had put together into one single large SMPL file yielded better performance. So if you're not working with multi-threaded, this gave us better performance, but obviously there's also some issues with this if you use that. Julie can go into details, but I really need to jump further ahead of this, so I'm just going to skip those details. Then we use multi-threading. This uses regular grep. Each CPU gets a bucket of files. The way the Kernel multi-threading works is that you basically give it a directory. Kernel then splits it up, let's say, between the number of threads that you have. And for each thread, it says, here are your files, here are your files, here are your files, and it starts working on that. Does that make sense? Okay. So with this strategy, we ended up seeing that sometimes some CPUs actually ended up, basically just running out of things to do fast. So then we just increased for each CPU, we gave it 3 threads. And that seemed to help, but this is not ideal. And after some discussion with Julia, we use coxygrep. Coxygrep basically is an option that you can give to Coccinal, which takes it basically splits up the same stuff again, but it will force evaluation of the rules to files at the start. It will only kick off a worker on files that it knows are applicable after. Issue, not all buckets are created equal, so CPU can go idle towards the end. So this is great. You're going to see the CPUs go all crazy. You're going to see them working and doing a lot of work. But eventually, some of them may actually start dying down completely, but that's just towards the very end of your job. But it happens. So the parallelization improvements, you can use ID utils. GNU releases it, Free Software Foundation, so forth. Glimpse is another tool that you can use as well. And the unfortunate aspect about Glimpse is that it's actually a proprietary tool. I recently poked them, though, and the news that I just got yesterday is that they're going to open source it. So it's now going to be released under the IC license. By default, it uses grep. You should be using coxygrep for sure. There's also other optimizations that you can work with. So, for example, there's a needle in the haystack stuff, which I'll get into next. Not everyone wants to index their trees, though. I mean, I don't. I just don't want to use any of these tools. I just want to use regular Coccinal and just get pull and get fetch and so forth. So use coxygrep. Not all buckets are created equal again, so that needs to be addressed. Julie indicated now that there is work in progress right now to actually integrate full parallelization, so that way you don't have to split off and run different scripts or something like that. That'll basically be using OCaml parmap. And Roberto de Cosmo had implemented this. So this is all going to be reworked and merged and so forth. In the meantime, however, we've come up and brewed a series of options and things that were ideal for us. And we basically stuffed this into a Python script, and this was generalized. So you essentially don't have to use that shell script, but you could just use pycoxy, and it does basically what you'd expect, which is basically it uses also the in-place argument, which basically modifies the changes directly to the tree. So because you're using Git, you don't really need to watch Coccinal spit out what it should change, but actually it should just change it and then do git diff, which I think is a lot easier to review. So if you're interested and you want something that just has all these options already and makes it easier for you, you could just download pycoxy. It's part of the Backports project, and basically, eventually we'll phase that out once we have full parallelization support integrated into Coccinal. Here's another tool that we ended up using in some of our rules. The idea is that you don't actually want to modify at times, but actually tell Coccinal that you have a specific rule that expresses what type of things you want to change. So, for example, if you want to modify a PCI driver, then you can say, well, look for a module device table. And if you see it in a file, that's a PCI device driver. Okay? So we would use this, for example, with it depends on module PCI. So now we're going to make this rule, but it's going to depend on this guy. So it's only going to do this modification for PCI drivers. And this backports the PMOps collateral evolution that was added to the kernel. So we basically provide our own callbacks here, and basically we also just do an if-def, and for the old kernels we just do the suspend calls. For the new kernels we leave the PMOps. So again, this depends, well, this doesn't show it depends, but it should have depended on the module PCI driver. In this case, we actually also use some fresh identifier thing that basically allows us to also concatenate some string, add some suffix to our routine. All right. So another point I'd like to make is Coccinal helps with precision. Julia went into an example of this, but I'll just go through it fast. You can get the code here if you want to test this yourself, run these commands. This is basically just going to apply one coccinelle rule. This is going to apply a second one, and you can just check the diffs to see what it does. The point that I like to make is essentially that if you have two types of data structures that are named very similarly, right? Just as one is bubble ops, the other one is net device ops. And if you, let's say we had this other data structures here just declared, it's basically just both of them are using net device. And then you have some code like this. Most of them use the struct net device, the other one uses bubble ops. There's two ways to express a change, for example. One is with expression, the other one is with struct. If you use expression, you're going to get one set of rules. If you use struct net device, you're going to get another set of rules. If you use the expression, you are basically going to end up with all the fields change whenever something called net dev ops is found, even the bubble ops, right? But if you use struct, it's a bit more precise and it doesn't modify the bubble data structure. So if you use something like sed, for example, it would be limited and it might end up changing this for you. You can't do that with sed. You could do this with coccinelle and be very precise. And I think some folks who are concerned about consistency should obviously, I think, get a kick out of that. Some empirical overview now of usage of SMPL. We removed support for older kernels. So now, we used to have a lot of SMPL rules. We shaved down support because we needed to start trimming things down. Now we only have 5 SMPL patches and backports. Only 5. It's overkill to use coccinelle for really small patches. And the reason is that you're only using it for one change for one driver. It doesn't make much sense to formalize that yet. Using coccinelle is ideal then for the complex backports, the really hard shit. That's what you want to use coccinelle for. You must break down every patch into separate atomic pieces. This is a requirement, and it's a good practice. Unfortunately, we at SUSE also work with this strategy. Now we've made the first set of changes, kind of like the static inline stuff. I didn't know whether or not this was going to be accepted, but I submitted a set of changes to backport a new subsystem that would allow us to backport with less amount of work. It got accepted. It's now merged. Now we have at least some precedence for allowing us to make changes into the kernel that would hopefully allow us to backport things automatically. What those things are, we're still trying to figure those things out. But static inlines are a perfect example of one of those use cases. So the backport module and the headers are just one level of helping with automatic backporting. SMPL backports, an SMPL patch backports one collateral evolution. If you backport the sum of the required collateral evolutions for one complex subsystem driver, it implies you can backport new subsystem drivers automatically. Does this make sense? So there was a question earlier about Julia about threaded RQ and if it went well. The answer to that is that you would need to address full backporting of that device driver and all the collateral evolutions for that device driver to a target kernel in order to get the gains of full automatic backporting for that device driver. So what I try to do, for example, if someone is going to try to add a new device driver, well, I really would prefer if those patches were atomically split up. Then I hope that the next iteration, they would formalize SMPL for them. And the reason is that if you do that, then you could throw another device driver into the backport string. It'll basically pick it up and then apply SMPL on it. And if you address all collateral evolutions for a complex driver, you should be able to backport simple device drivers for that subsystem automatically. Does that make sense? Okay. Can we do better? Hell yeah. So what's our bottleneck here now? So each collateral evolution upstream is an atomic. It is atomic, right? It's hard to learn SMPL, too lazy to write SMPL, perhaps. So a tool to infer SMPL grammar would be ideal. I'm not going to get into that, and I'll let Julia perhaps talk about that But it would be ideal if you could infer SMPL from a series of patches. Each respective collateral evolution commit should have a respective SMPL grammar rule. It poses a new challenge to Kernel then, because if you think about it, reverting an SMPL grammar rule won't actually suffice to backport that, because you want it to work for the new kernel, but also the older kernel. At least for backports we do. So you don't want to revert the change. You want to revert it, but with an if-def. And that's a bit more complex. You want to basically say, well, this is what this should apply in this universe. This is what this should apply in this universe. And this is where the compat module helps, because you hide the complexities of different kernel revisions in a shared header files and a compat module, and you basically just try to target now this shim layer, and you basically try to keep the code as upstream as it is as possible. Remember that the atomic patches that you write for backports then are basically the last resort. The goal of the backports project is that you should keep the source code as pristine as possible with the least amount of modifications. And everything should be dealt with a shared header file and compat module. Now, another thing. Assume collateral evolutions now can be expressed from the start with SMPL. Would that help us? Well, you don't need inference then on the SMPL grammar, but we already have it because whoever wrote a collateral evolution wrote it into the patch. And can we do something with that? We're not sure, but there's some ideas. Can we do better? So what if we do try to strive for self-programming of the backports module? How would we accomplish this? One idea would be, for example, for you to have a database of SMPL grammar rules reflecting possible collateral evolutions in the kernel and possible respective transformations that those collateral evolutions, implied that you needed to make historically on your backports module. So if you have a correlationship of how you already backported a specific SMPL grammar rule to a specific change in your compat module, you should have a database of what that change should look like and what you should be doing now to backport this specific change onto your original code or into the backports module. The way to upkeep this then and to scale this would be on every single day you try to infer the SMPL grammar rules from Linux Next. And if you have a match, then add it to your backports module. Is this possible? It's theoretical right now. But so was adding SMPL for backporting. But it was possible. So whether or not this is realistically doable remains to be seen, but I think it's possible. And remains to be seen, of course. But so I'd like to thank Inri and Ariel, of course, for allowing me to participate in the reel and with Julia and working on this. And are there any questions? Yes. So it's atomic patches. And I could actually just show you exactly what that looks like because it's a bit hard to understand, I guess, unless you see it. We apply the legacy patches first. And we break these down by subsystem. And we basically define them through a number, and we define them through a name, which should be reflective of the specific collateral evolution. I don't see why not. No, actually, no, because this would basically be dependent upon the history of how we started collecting the patches. So if you apply the SMPL patches first, there may be some hunks that no longer apply. Because remember, Kernel is the one that does the magic of allowing you to skip some of the hunk rework stuff. So it lets you do all the magic and not have to deal with conflicts. I'm sorry, say it again.
Why do you
Oh, because see, so we want. Well, so say you're on 2616RC1, and for some stupid reason you just want to use backports for that. I mean, you could use that. We could certainly remove the code for that specific kernel, but I think it's a lot clearer for the developers to look at the code and see what was left for the new kernel and just see the if-defs and so forth. But again, the magic is dealt with really within backports module itself and within the series of header files too. So the delta really should actually only address the components that were impossible to change within the backports module or through the header file. So essentially, each of these patches basically should reflect things that we just could not add into the backports module or header files. I call a bit bullshit on that though, because I think people are sloppy, and a lot of these patches are also old. I've been trying to be a bit more strict with accepting patches and so forth, and asking people to be more atomic with these changes. And I think that quite a lot of these patches could be transformed into respective changes into the compat module and backports module. So again, if we could automatically do the transformations into the backward module, that's another level of automation and would require less work. That's correct. It basically is just completely linear. We have the histories for a long time now. I'm sorry, of the what? Those are basically just tarbles that we upload into kernel.org. That's correct. There's some folks, however, Intel is one example, who uses the backports framework to actually keep a monolithic kernel and basically just evolve it and then do rebasing whenever they need to. So Intel does that, and it works for them because basically it means that some other developers don't really need to actually learn how to work upstream, and then you have a few people who basically just do the development and then upstream the patches for you. So it works really nice for some people, and backports allows you to do that as well. It's just an option. Any other questions? If you wanted to backport to one target specific kernel, let me indicate at least one caveat so far is that right now we only provide backports for device drivers. In-kernel support is yet to be developed, but it should be relatively easy. Targeting one specific kernel would basically entail removing tons of, trimming down the compat module significantly. Or basically wrapping the inlines into code itself. That I think would be really hard. At least it would basically just deviate completely from the current progress of the project, I think. So it would essentially be just a completely, it's a definitely different approach, but it certainly could be done, for example, if it's desirable to not have, I mean, see, that's the thing. I think that the backports, a shim essentially helps because you end up with less patches, right? And that's important because you would then avoid conflicts with quilt, refreshing, and basically what you want to do then is make your SMPL evolutions as simple as possible too. Having SMPL Express, for example, threaded RQ support, using the inlines and all that stuff in code, it would be a bit more complex. So the backports module and series of header files allow a simpler backport to be done and expressed. So one thing that I could think of, for example, would be to target, I know Red Hat does this too, so they basically just take some of this stuff and they just modify it to their need. And that's essentially it. And the reason is that we already backport some collateral evolution, so if you need to backport something, you may want to check if we already did that. Again, we only cover certain specific subsystems, so then we don't cover every territory that everyone would be interested in. Mm-hmm. Mm-hmm. Uh, can you repeat the question again? Mhm. Um, s- well, so if this strategy seems of interest, essentially, I think with the kernel source tree, one of the things that I could think could possibly be done is to start throwing into a shim, for example, a specific. Uh, let's say we would have, we might have, for example, directories then for sharing specific types of patches that backport one specific type of collateral evolution. Once you have that, then you basically can visually see that this is one collateral evolution that's being backported amongst different device drivers or different areas of the kernel. You would identify the respective upstream commit. Then the second step would basically be, can this directory, now that expresses this collateral evolution, can we express this in a header file or a module to trim it down further? Once that's done, then you have a simplified version of that. And then the next question would be, can you now write this in SMPL? Device driver or one little change here. But for the series of changes that are long and repetitive amongst a series of subsystems, for example, it would make a lot of sense. And this is exactly what we do with backport. So we don't strive for coccinal for um, every single uh, series of patches. We only do that for things that we can probably share amongst device drivers. So here's another one, for example. Uh, what is it, diff or something like that? It, syntax equals diff. So this is one, for example. So it's really for things that are really intrusive, but can be that one indicates or that one sees that is widespread amongst a series of components in the kernel. But in this case, for example, it's a new argument to a data structure, right? I mean, to a routine that's a callback, right? So that's something that could be generalized if we're essentially backporting this whole new collateral evolution, for example, to a series of files. So that would be one way to go about things. Yes. So for those, we basically just don't backport them. And in fact, the interesting, I mean, it's possible to backport those changes. It's just that we haven't added in kernel integration support. What that would require, I'm sorry. Oh no, we just essentially we run into those issues. We just don't backport those device drivers or whatever. Yeah, we just say no. For example, regulator was one subsystem where we ran into a lot of issues really fast. Um, and again, one of the strategies there was to try to tell Android folks, hey, you guys don't really need to be doing all this random funky stuff with your trees. You could just use something like this for your development workflow and not have to branch out and whatever. But the regulator subsystem had a lot of internal components that essentially were not modular. So right now, backports for modular components. It should be possible to allow you to backport in kernel. So the way to go about that, at least the way that I would see it, is you would essentially take the code, dump it into a new directory. Now you have a series of new directories, and you just basically add a kconfig option. And now you have the code merged part of your own kernel. Now you can compile the entire kernel with these other device drivers from a future version of something. And this is why I was looking into the concept of K-graph and the universe stuff to see whether or not something like that could be used for different types of universes here. Or another one would be module namespaces, for example, that Andy Clean had worked on a few years ago. But again, these are just thoughts. This is not developed yet, but it's certainly, I think, doable. And there are certainly ways to categorize the types of changes that we'd have to backport. And I think that's actually what we would have to end up doing to try to automatically write a compat module, for example. We would need to probably identify the different, through history, the different changes that happen in the kernel, identify the categories, and identify what type of SMPL grammar those typically look like. Mm-hmm. So that actually, those require sometimes really manual investment and time to look into how older functionality was working with this feature, for example. So typically that just requires inspection through the history, you know, and reviewing how things were done before, understanding the code, and seeing perhaps if there's ways to backport the feature. One example would be threaded RQ support. In that case, there was no obvious way to do that, but we saw how it was implemented in the kernel. So, well, you know, like, well, we could just create a single threaded work queue, and it's an example where you actually have to be a bit ingenious, and you can't really. I mean, you could probably infer how to backport such a thing in the future, but that's only because we now have history that we've done it before. So namespace was something we dealt with as well, and I think that basically we just disregarded the namespace stuff. And I think for some subsystems that worked, some other components, I think that obviously wouldn't work. But for those cases, it basically just mean that you wouldn't have the functionality you'd expect. You basically just wouldn't get the namespace support for older kernels. Yeah, pretty much, yeah. But we would ignore certain things. So, for example, we know that the older kernel just basically has no notion of namespaces, and we can't make any use of it. So basically, just work with the current namespace, right? Any other questions? Yes. That's also. Sure. Absolutely. Sure. Any other questions? All right. Well, thanks.